Good morning, iPad students. This is just kind of an informal chapter review discussion to try and help you out with the chapter review a little bit, review for the test, so on and so forth. So I'm just going to discuss some things from each section, kind of the highlights of it, kind of keep it kind of short so that you can have plenty of work time and you can use this video as you see necessary. The first section is section 1.1, which was about points, lines, and planes and how to name those, how to identify them, what they are. So you might look over some vocab for this. Points is, all three of these are things that are undefined in geometry. A point is just a location, no size to it whatsoever. A plane is a flat surface that extends forever and ever in every direction, and a line is a series of points that are very, 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 very close that extend forever in just two directions. Alright, well, how to name points is we actually just write point and name it with a capital letter. So like point A here. Alright, how we name a line is we can either write the word line and we use just 2 points on the line. We don't use 3 points on the line. So we can name it line BC, or it would be the same line if I called it BD. It's going to cross through those points and keep going in those two directions. To name a plane, I name it with 3 points that are on that plane. So I'm going to name this one plane A, B, C. Now there is also some other key terms in here, for instance, collinear. Well, collinear are just things that lie on the same line. So like points B, C, and D would all be collinear points, where coplanar would mean that they are all on the same plane. So actually, most of these points up here that I could name would be on, plane A, B, C, for instance. So I could name point A, point B, and point C would all be coplanar. Now, if I had those 3 points and point E up here, those would be non-coplanar, because I couldn't fit a sheet of paper that would pick up all of those 4 points without having to bend that sheet of paper. So another thing that we talked about was rays. Now rays has an endpoint and extends in one direction forever and ever. How we name a ray is just with a ray above, you have to list the endpoint first. So if I was talking about this diagram, C could be the endpoint of my ray that passes through D. That would be different than ray CB, because now C is still the endpoint, but it goes the other direction. These are what we'd call opposite rays. I think that was the main highlights from section 1.1. Section 1.2 was over measuring and constructing segments. Now remember, a segment is just a piece of a line, so it's going to have 2 endpoints. And that's what a segment was. Remember that this section started off with the problems that was from the number line. Well, that's a pretty bad number line there. I think I can do better than that. So let's see here. Get this up here. So we had that number line. And we would be given some points on that number line. Let's say this point right here, and it's at -3, and let's say we have a point B over here at 5. Well, if they just wanted to know the length of AB, remember they just name it with the 2 capital letters, and we could just count it over until we get to the point. So we could just count 8, but the actual formula was the coordinate of A minus the coordinate of B and take the absolute value of it. So by formula I'd have -3 minus 5, which is -8. The absolute value of that would just be 8. So that's kind of how the section started, and then I think they started talking about one of the famous postulates, which is the segment addition postulate. And remember, postulate is just something that is assumed to be true without actually proving it. So let's see, if I get a segment up here, what the segment addition postulate would say was if I added the two small pieces together, then it would have to equal that big piece. And a lot of times they'll work this into some sort of equation, like this piece might be 5x and this piece might be 10x, and that whole thing equals 60, let's say. So we know if we add the two small pieces together, that has to equal the larger piece. So then we can solve for x. And remember, if it's wanting the pieces or the lengths of the segments, what we would have to do is plug that value back in for whichever piece that we're looking for. So 4 times 5 would give this piece 20, which would make this piece over here 40 to equal to 60. So the angle addition postulate was also in there. Look over your notes on the constructions to review on that real quick. We're going to go over section 1.3, and in this section it was almost the same thing, but it was measuring angles and constructing angles. So again, look over your notes on constructing angles. Let's talk a little bit about measuring. Remember, they introduced the protractor on this one. So remember, to measure an angle, you've got to, whatever your angle is, you've got to put the vertex right at the center of your protractor, kind of like so, so that one side length faces at 0, and then you can just see where that opens up to get your measure. That looks like about 38 degrees right there. And then I think it also talked about acute, which is less than 90, right angles, which is 90 degrees, and then obtuse angle, which is between 90 degrees and 180 degrees. It also probably had the straight angles, which is a straight line, which has a 180 degree measure in it. Also, they talked about the angle addition postulate, which is very similar to the segment addition postulate, in that it says that the two small angles, like let's call this 3x and this 6x, add together to equal your big angle. And let's just call that, looks like about 120 degrees to me. Alright, so if we added the two small pieces together, that would have to equal the big angle. So let's see, 9x equals 120. Made this one up, so it's not going to turn out nice and even, it looks like. What can I take out of this? A 3, which would make 40 over 3. And that's as far down as it looks like it would go. Now remember, you would have to plug this back in for the angles to see what each one of them was. So in other words, you would have to take 3 times 40 thirds, so that works out nice and even, because this angle would just be 40 degrees, and it looks like this angle then would have to be 80 degrees. Okay. Alright, section 1.4 talked about pairs of angles. Alright. So this talked about the adjacent angles. Remember, adjacent angles are two angles that share a common side. So angle 1 and angle 2 would be adjacent angles. Well, if those two adjacent angles was to form a straight line when I take out that side, that's what we would call a linear pair. So if they would add together to equal 180, they would be a linear pair. So that was in section 1.4. And then also complementary angles, which is just two angles that add together to equal the 90 degrees, was in there. So these would be complementary angles. And then the two angles that add together to equal 180 degrees we called supplementary angles. Okay. So if I was given one angle, let's say it was 60 degrees, well, its complement, I would subtract the 60 from the 90, and that would give me 30 degrees for its complement. Works the same way for supplementary angles. Section 1.5 was using formulas. So some of the formulas was the triangle formulas, and remember for the perimeter you just add up all the sides. The area of a triangle would be 1/2 base times height. Then we had the square, which again the perimeter, you're still going to add together all the sides, or you could take 4 times the side length. And the area would be side squared. Well, there was the rectangle in there also, and again the perimeter, you're just going to add up all the sides, or you could take 2L plus 2W. And for the area is just length times width. And then your circle formulas were also on here. And remember, all the way across the circle is the diameter. From the center to a side is the radius. And all the way around the circle is the circumference. Well, they gave you the circumference formula as 2 pi r, or just pi times the diameter. And the area of a circle would be pi r squared. Section 1.6 was the midpoint and distance formulas, and we also incorporated using the Pythagorean, graphing out a couple of points and using Pythagorean in place of the distance formula. Okay. So your midpoint formula, well, was the average of our x values, so x1 plus x2 divided by 2, and then the average of our y values, y1 plus y2 divided by 2. And our distance formula was a square root of x2 minus x1, that quantity squared, plus y2 minus y1, that quantity squared. And again, Pythagorean we also used in this section, which is a squared plus b squared equals c squared, and it gave us the same answer as the distance formula did. And then in section 1.7 we talked about the transformations. We talked about preimage and image. The preimage comes first, the image comes second. We talked about mapping a point with arrow notation. For instance, a translation moving it 2 to the right, and then down 3 would be this arrow notation here. So we talked about a slide being a translation, a turn being a rotation, and a flip being a rotation. We also talked a little bit about a dilation. So I'm going to go ahead and end this video. This will be your review video for Chapter 1 review. Use as necessary.